Alright, this is our last video on periodic trends, and this is going to be a pretty short video. We're going to talk about electron affinity. So, in my mind, electron affinity is sort of the opposite of ionization energy, right? Whereas in ionization energy, we're taking an electron away from an atom. With electron affinity, this is the energy that is given off when we add an electron to an atom. And while ionization energies always require energy to take an electron away, when we add electrons to an atom, that generally is an exothermic process. We're giving off energy. Energy is released when we add an electron. And so some way of thinking about electron affinity is the more negative the electron affinity is, the greater the magnitude of that negative sign is, the more that electron wants additional electrons. And so the general trend is sort of the same as we have for atomic radius and ionization energy. As we go up and to the right in the periodic table, the atoms get smaller, and so the electrons are able to get closer to the nucleus, which they like. And the ionization energy increases. It's harder to take electrons away. And so not only is it harder to take them away, they also are more likely to want electrons. And so as we go from left to right across the periodic table, we say the electron affinity increases, but I'll say, right, it increases in magnitude. Electron affinities are negative, so the more negative it is, the more that electron wants atoms. And so electron affinity increases in magnitude as I go from left to right, but it's actually becoming a more negative number. And these trends kind of make sense based on what we know about the properties of metals and nonmetals. Right, on the left-hand side of the periodic table, the ionization energy is relatively small, meaning it's easy to take electrons away from metals, or at least easier than from things on the right-hand side of the periodic table, the nonmetals. And we know that metals like to form positive ions, so it would make sense that they would have low ionization energy. It's relatively easy to take their electrons away. And I think it also should make sense that nonmetals tend to have large electron affinities, right? Large negative electron affinities, right? When they form ions, they like to form negative ions. So it makes sense that they want electrons more than metals do. So they have a higher electron affinity. Now, with ionization energies, we explain some of the exceptions to the general trend based on electron configurations. And for electron affinities, there are even more exceptions, right? If you really dig down and start looking at some of these values, it's kind of all over the place, right? In general, as we go up and to the right in the periodic table, the electron affinity becomes more negative. It becomes a larger negative number, but there are all kinds of exceptions. If we think about the halogens, for example, even though they're the farthest to the right, they do not have large negative electron affinities because they have completely filled subshells. Right? They do not want to gain any more electrons. They're very happy with the number of electrons they have. Right? Same thing with nitrogen. Nitrogen is pretty happy because it has the P3 subshell. It has a half-filled subshell, so it doesn't particularly want to add any more electrons, at least when it's in the gas phase. So the electron affinities are for gas phase elements, right? Once I've put these things into ionic compounds, right, a lot of these predictions from electron affinity kind of go out the door. And so that's why this video is kind of short. In general, as we go up and to the right, electrons want more, or atoms want more electrons, but we're not going to dig deep into the trends. And I generally don't even ask about trends of electron affinity because there are so many exceptions. As long as you know that generally, as we go up and to the right, they want more electrons.